Two videos, no labels. Can AI figure out exactly what's happening and when in each one? In this paper, we introduce the first unified model that does both, aligns video frames and segments actions, fully self-supervised. Video alignment means figuring out which moments match across different videos, like syncing up two people making coffee step by step. But it's hard. Real videos vary in angle, style, speed, and are full of messy, unlabeled frames. Here we present an alignment result from our approach. The query video on the right is aligned with the reference video on the left to produce the aligned video in the center. Despite the two videos depicting clearly different objects, the alignment is visually consistent, demonstrating the effectiveness of our approach. Here is another example where the reference and query videos capture the same action from different viewpoints. Despite the change in perspective, the video in the middle appears perfectly aligned with the reference. Action segmentation breaks a long video into meaningful steps, like crack egg, whisk, pour. The catch? Actions can look really similar, boundaries blur together, and clutter in the scene just adds to the confusion. Here we present our action segmentation results on a real-world task. At the bottom, we show the segmentation outputs, the ground truth, our model WASOT, and the previous state-of-the-art ASOT, respectively. Each color represents a distinct step in the activity, and the red arrow indicates the position of the current frame within the segmentation. As shown in the video, our model segments the actions more accurately and clearly than the previous state-of-the-art method. We address the challenges involved in action alignment and segmentation with fused Gromov-Wasserstein optimal transport, which aligns frames by combining visual similarity with temporal structure. This framework lets us handle variations in speed, order, and background while keeping the alignment consistent. We jointly optimize video alignment and action segmentation losses so one task reinforces the other, boosting accuracy and cutting down the cost of training separate models. The first novel method we introduce is VAOT, Video Alignment Optimal Transport. Given a pair of videos, we begin by extracting frame embeddings using a shared encoder. Next, we compute the cost matrix CXY, which quantifies the visual differences between the frames of the two videos X and Y. We feed this cost matrix into our two-part VAOT module to align the video sequences. The first part encourages frames that look similar to align, while the second part makes sure that alignment also respects the temporal flow, so actions stay in the right order even if styles or speeds vary. The VAOT module outputs pseudo-labels TXY star. These pseudo-labels serve as supervision signals for training the shared encoder. We optimize the encoder parameters by minimizing a cross-entropy loss between the normalized similarity matrix PXY computed from the frame embeddings and the pseudo-labels TXY star generated by VAOT. For joint video alignment and action segmentation, we introduce WASOT, which combines our VAOT module for video alignment with ASOT for action segmentation. WASOT extends VAOT by incorporating action-specific cluster centers A, initialized with k-means. In addition, we introduce new matrices specifically for action segmentation on videos X and Y. Both the shared encoder parameters and the action embeddings A are trained using a combination of self-supervised learning losses, the video alignment loss LXY, and the action segmentation losses LXA and LYA. For action segmentation, LXA is the cross-entropy loss between the normalized similarities PXA, computed between X and the action embeddings A, and the pseudo-labels TXA star obtained from ASOT. Similarly, LYA is between PYA and the corresponding pseudo-labels TYA star from ASOT. Together, these losses enable joint optimization of the encoder and the action embeddings, enhancing both video alignment and action segmentation in a self-supervised manner. We achieved a significant improvement on phase progression, phase classification, and frame retrieval metrics over previous state-of-the-art video alignment models. We also demonstrate that our approach outperforms previous methods, such as LAV, in frame retrieval. Given a query frame showing a person with the bat swung back, we retrieve the 5 closest frames in the embedding space. As shown, VAOT consistently retrieves frames corresponding to the same action, whereas LAV does not, as indicated by the red circles. We also achieved substantial improvements in mean intersection over union, mean over frames, and F1 score compared to previous state-of-the-art action segmentation models. By unifying video alignment and action segmentation in a single framework, we achieve stronger performance with fewer resources. We believe this opens the door to more scalable, label-free video understanding. If you're curious, check out the full paper or feel free to reach out. We'd love to hear your thoughts.